Okay, so here's the solution to test number 3. So I asked you to plot the exponential function, include at least 4 key points. So I had this table that I gave you, and I gave you one extra column there, so let me undo that. Okay, so the exponential function has a base of 2, so we have f of x equals 2 to the x. So we've got this table which is x and f of x, or y. So the numbers we pick are 0, -1, 0, 1, and 2. So this is 2 to the minus 1 power, which is 1/2, which is 0.5. We have 2 to the 0 power, which is 1. 2 to the first power, which is 2. 2 to the second power, which is 4. And you could include a third one, which would be 2 cubed, which would be 8. So we can plot those on the graph. So let's go from, I think I gave you some numbers here, 10, -10, 10, -10. So we plot -1, 0.5, 0, 1, 1, 2, 2, 4, 3, 8, and then you draw it. You need to make sure that you don't cross the x-axis there, that you see that asymptote. And that's it. Okay, so that's the first problem. Okay, the next one is a logarithmic function. It's a log to the base 3. So f of x equals log base 3 of x. Okay, so we make up a table. Same kind of deal. We need at least 5 rows because we got 4 points. So we've got x and we've got f of x. Now, the easiest thing to do here is to go the other way. So we're going to do -1, 0, 1, and 2. And so, logarithm says, what power do I need to raise 3 to get a result? And basically we go the opposite way. So here we have, we're going to have, to generate this table of x versus y, we're going to have 3 to the -1 power, 3 to the 0 power, 3 to the first power, 3 to the second power. So we'll get 1/3, 1, 3, 9. And it's because logarithms and exponentials are inverse functions of each other, so you can kind of switch the points. So what we do is we plot these 4 points. So we have x equals 1/2, or 1/3, y equals -1, so it goes right there. We have x equals 1, y equals 0, which is that point. We have x equals 3, y equals 1, and x equals 9, y equals 2. And we have this vertical asymptote here at x equals 0, and they all have the same shape. So once you get these 4 points in there, you can draw a pretty good curve. Okay, so that is it for logarithms. Just remember, for exponentials, it's -1, 0, 1, 2, maybe 3 if the base is 2. For logarithms, you put -1, 0, 1, and 2 in the y column, and then calculate the x's. If you just, what some people do is they'll pick 1, 2, 3, 4 or something for x, and it just won't give you enough data points to give you a good curve. So that's why you do it that way. Okay. So number 3, we have that the function is e to the x, f of x is e to the x, and then we have the transform function, which is -e to the x. plus 2. So we have x and y shifts, we have reflections across the axis, and that's pretty much it. So the x shifts are in the exponent, and the y shifts are the constant that's added on. So we could say shift plus 2 y direction. So that would be, that's your parent function. You're adding 2, so you're going to shift it in the y direction. And then you have a negative sign here, which is a reflection. And if the negative is out in front of the exponential, that means it's an x-axis reflection. Now if I had e to the minus x, where the negative is in the exponent, then it would be an y-axis reflection. So that was all there was to that one. Then we had the next one, which is logarithms. So you have f of x is the natural log of x. That's, natural log is base e. Notice I have negative x plus 2. So I've got a number here, I've got some kind of shift, and I've got some kind of reflection. Now, I don't know how many times I have to tell people this, but most people don't pay attention, but you need to factor out this negative sign so that you divide both of these by -1, and what you'll get is that. So you'll get negative the quantity x minus 2 instead of negative x plus 2. And you can see it works out. If I multiply this out, -1 times x is negative x, -1 times -2 is positive 2. Because in this form, you can clearly see what the shift is. And if you don't show this to me, then I'm assuming you cheated and just plugged it in the calculator. Okay, so because this constant is connected to the x, it's going to be a shift in the x direction. So we say shift, and it's always x minus h, but plus k. So if you remember back to quadratic equations, or just to shifts in general, so the shift here would be plus 2 again in the x direction. And because the negative sign is inside the argument, that's going to be a reflection, and it's going to be across the y-axis instead of the x-axis. So here, if it's outside, if this were negative, the natural log, then it would be an x-axis, but it's the natural log of negative, then it becomes a y-axis reflection. Okay, number 5, just a little, not only do you have to talk about the transformations, but you have to show both functions, both f of x and g of x. Okay, so let's talk about the actual things happening. You've got a negative sign out front here. That's x-axis. So we got x-axis reflection. We've got x plus 2. So remember, it's x minus h. So in this case, the x shift is going to be plus or minus 2. And then we have this constant out by itself, so the y shift is also minus 2. So we're going to apply that information to our graph. So we're going to draw the parent function, which is log base 2 of x, which I think we did earlier, didn't we? Or did we do log base 3 of x? No, I think it was log base 2, log base 3. So, you probably need to generate a table here with our 4 points. And because it's a logarithm, we're going to put -1, 0, 1, and 2 here. And we could do 3 because of the base of the logarithm. So this is x, and this is going to be y, which is equal to log base 2 of x. So this is going to be 1/2. It's going to be, it's going to be 2 to the negative 1 power, which is 1/2. Then you get 2 to the 0 power, which is 1, 2 to the first power, which is 2, 2 to the second power, which is 4, 2 to the third power, which is 8. So there you have 5 points. So we go x1/2, y equals negative 1. X equals 1, y equals 0. X equals 2, y equals 1. X equals 4. 1, 2, 3, 4. Y equals 2. And x equals 8, y equals 3. Again, the logarithm has this vertical asymptote that comes up here. That's why we only need this 1 point. And then we go through there and we come over. Okay, so that's our parent function. Now the first thing you do is you always do the reflection first. So what will happen is these points that are above the x-axis will go below the x-axis, and the ones that are below the x-axis will come above the x-axis. So you see how these are reflected. So that is just the reflection. So if this is log base 2 of x, this is minus log base 2 of x. And then finally you're going to shift it 2 units in the negative x direction and 2 units in the negative y direction. So if we take all these points, the red points, and we move them -2, -2, like that. So that's this one. If you take this one, -2, -2, you get there. This one is -2, -2. This is -2, -2. You're going to have a vertical asymptote here at -2. Now this point here, which is at 1/2, +1, you go -1, -2, -1, -2. That comes right there, and so this thing is going to look something like that. So that's how you do that transformation. Okay, the next one is using partial fractions, and so we have this initial expression, and what we're trying to do is rewrite this rational expression as two fractions, but the first thing you have to do is you always have to factor the denominator. So we have what two numbers multiplied together give us 4, 4 and 1, 2 and 2. Which one has a difference of 3? Well, 4 and 1 does, so we're going to have 4, we're going to have 1. And one's going to be positive, one's negative, because we have a -4. So it's either +4 times -1 or the other way around. But the sum of the inner and outer terms is -3. So that means I have to put the negative on the bigger one of the two. Okay, so that's the factored part. Now, then what we do is we say, okay, well, we want to create two simpler fractions where you have the two factors like that. So we need to then combine these two that we've now separated into a single fraction. And if you have two linear terms, you can just kind of cross multiply to get the numerator. So you get a, which is the numerator here, times the denominator there. And then you take the numerator here and multiply by the denominator there. And then you multiply the denominators together. And you can see that, well, I didn't write it out here, but you know, this is the same as that, so they have the same denominator now. So you can set the numerators equal to each other. And the question is, what do A and B need to be to make this thing work? Well, the easiest way is to choose x to be one of two values. The one value makes this go to 0, and the x value that makes this go to 0. So -1 plus 1 equals 0. 4 minus 4 is 0. And then you plug it in. So you'll have 2 times -1 minus 3 is equal to a times 0. Because if I plug -1 in here, -1 plus 1 is 0. And then you have b times -1 minus 4. So over here we have -2 minus 3, which is -5. Then we have b times -1 minus 4, which is -5. So you can see b is equal to 1. And we do the same thing here. Plug in x equals 4. And what happens then is this term goes to 0. 4 minus 4 is 0. So you have 8 minus 3, which is 5. 4 plus 1, which is 5. So a equals 1. And so it says, change the following expression into two fractions. So just solving for a and b wasn't enough. What you need to do is to take the original rational expression and then plug in the a and b that you have found in the previous step. So that's the answer I was looking for. Okay, now on to lots of more logarithmic stuff. So this is number 7. And I asked you to expand the following expression. A lot of you got this pretty close to being right, except this last step, which I'll show you. So if you have a product and a quotient, you take all the ones that are in the numerator, and those are positive. Make sure the base of the logarithm stays the same. And what's in the denominator is subtracted. Now, I'm not going to pull the exponent out yet. I'm going to rewrite any square root or any root as a fractional exponent. So the square root is the same as the half power. So I can bring out the exponent now. And the one people mostly got wrong was that log base 4 of 4 is 1. So if these two are the same, then you can go one more step. Okay, next says write the logarithmic expression in exponential form. So, or exponential and logarithmic form. So remember, the base of the exponent is the base of the logarithm. The answer is the argument of the logarithm, and the exponent is the right-hand side. So the base is always easy because you can just put the base right there, and then you just switch the two. This goes to this side, this goes to the other side. And what it's asking is, what power do I raise 2 to get 16? And the answer is 4. 2 times 2 times 2 times 2 is 4. So this is the answer. It's just to reiterate why. Okay, number 9, going the other way. Log base 3 of 27 equals 3. So again, this is the base. This is the exponent. This is the answer. So we again switch these things over. This goes from the right side to the left hand side. The only place I have to put it on the right hand side is an exponent, because this base here is the same as that base there. So that's the answer. 10 e to the third power is equal to 20.0855. Now the base here, the base is e. Okay, so we take log base e of, again, switch sides here. So this becomes the log base e of 20.855 is equal to 3. But we would rewrite the log to base e as the natural log. So this is the answer. the natural log of 20. What power do I need to raise 2.71828 to get 20.0855? Well, it's to the third power. Okay, that's number 10. Number 11, going the other way, natural log of 7.3891 is equal to 2. So this is the same as log base E. And the reason I'm rewriting it as log base E is because then you can use the same logic as we did over here. So the base is E. The right-hand side becomes the exponent. The argument becomes the right-hand side. So E squared, that's E times E, is 7.8. Okay. The change of base formula. So our calculators only do log base E and log base 10. But the change of base formula says you can do either one. You can take the natural log of 24 and then divide by the natural log of the base. Or you can take log base 10, which is log on your calculator, of 24 and divide it by log base 10 of 5. So, and it says using the change of base formulas. It doesn't say use your calculator to do it. Okay. So if you do the natural log of 24, you get 3.178. If you take the natural log of 5, you get 1.609, or you can just do it all in your calculator one time. So you can do the natural log of 24 divided by the natural log of 5, and you get 1.975. You know what this is saying is that 5 raised to the 1.97 power should be equal to 24. So if I do that, every calculator has exponent stuff on it. 1.974, I get 24. Okay, now we're going to solve some equations. So we were saying that exponential equations, we can use any base for the logarithm, and the one that makes the most sense is the natural log. So we're going to take the natural log of 3 times e, 3 to the x minus 2.5 is the natural log of 24. And then you can bring that exponent down using the properties of logarithms. So we get x minus 2.5 is equal to the natural log of 24 divided by the natural log of 3. So let's go ahead and calculate that. And that comes out to be 2.893. And if you add 2.5 to both sides, so you take 2.8 something, add 2.5, you get 5.393. Okay. Okay, so an earlier problem was a expansion. This is a contraction problem, number 14. So we have 2 natural log of x minus 1 minus natural log of y plus 3 times the natural log of z. So when we did the expansion, the last step that we did was to take the exponents out, or to evaluate something like we had 4 times the log base 4 of 4, which was 1. In this case, we're going to move the exponents in first before we try to combine anything. So the multiplying factor out front becomes the exponent. And then what we do is now we combine them. So the ones that are positive go in the numerator, one that's negative goes to the denominator. So this is the natural log of this whole thing. So you have x minus 1 squared because it's positive. You have z cubed because it's positive. And you have y in the denominator, which is negative. So that's the answer. Okay, number 15. Most everybody got this one right. But Yeah, you can't take the natural log or log any base of a negative number. So it does not exist. The logarithm of -3, logarithm base 3 of -3 does not exist. Okay, turning over the page. So we have a couple of solutions for logarithmic and exponential equations. So number 16 says evaluate the following using the properties of logarithms. So in this case, we don't want to move the numbers in, we want to move the numbers out. So we'll have 3. The properties of logarithms says you can bring the 5 out as a multiplying factor, and you can do the same thing over here. But the natural log of e is 1, so you get 15 minus 14. So the answer is 1. So you need to show this work. Number 17, just exponential equation. Again, exponential equations, it doesn't matter which logarithm you use. Typically we would use the natural logarithm to change this exponential equation into just an algebraic equation. So you take the natural log of 5 to the x is equal to the natural log of 3.3437 and bring the exponent out. So there you've converted it to a algebraic expression. So x is just equal to the natural log of 3.3437 divided by the natural log of 5. And I think it's 0.75, but just natural log of 3.3437 divided by the natural log of 5. And you get 0.749999, so it's 0.75. Number 18. So here we have another exponential equation. Same kind of deal. Use the natural log. Bring the exponent out. Solve for x. Plug that in your calculator. Natural log 1024 divided by the natural log of 2. And you get 10. 2 to the 10th power is 1024. Okay, number 9 is a logarithmic expression. In this case, because it's a logarithm, you have to convert this to an exponential or use exponentials to solve for x. In this case, it is important what the base is, and the base is 6. So you take 6 to the log base 6 of x, 5 to the 6th, or 6 to the 5th power, sorry. 6 to the 5th power. So the log 6 to the log base 6 of x is just x, because 6 to the x and log base 6 of x are inverse functions of each other. And then you just take 6 to the 5th power, which is 7,776. Okay, the next two are these word problems. One thing a fair number of people got wrong was, it says the p is in thousands, so it's 548,000. So what you would do is you would see p of 0 is 548,000. P of 5 is 650,000. Okay, so you got to make sure you convert that. And again, one of these things you should be thinking about: would the population increase from 548 to 650,000 in 5 years? That kind of doesn't make sense. So then you should go back and read the problem and say, well, something's wrong here. Either you wrote the problem wrong or I'm interpreting it wrong. Okay, so what you do is you use p of 5 to figure out what k is. So you'd say, P of 5 is 650 is equal to 448 e to the k, but t is 5, so you put 5 in there. And now you just solve for k. So again, you have to have logarithm by itself or the exponent by itself. So we're going to divide both sides by 548. So we take 650 divided by 548, which is 1.186. So 650 divided by that will leave you that. And it's an exponential, so again, you take the natural log of e to the 5k is equal to the natural log of 1.186. That says 5k. You take the exponent out. 5k e, natural log of e is equal to the natural log of 1.186. This is 1, so you just divide both sides by k. So you'll get 0.2372. So that's k. So then you can go back and say P of t is 548 e to the 0.2372 t. Now we could check that out just by plugging in 5 to see if I've done this right. So we take 548 times e to the 0.2372 times t, which is 5, which is something that's not right. What did I do wrong here? Oh, I forgot to take the natural log of this thing. Yeah, so there you go. Good reason to try this thing out. Check the errors. Okay, so what is the natural log of 1.186? It's 0.1706. So if we divide that by 5, we get 0.03412. 0.03412. So I'm not going to take it for granted that I did it right that time either. So I'm going to take 548 times e to the 0.03412 times 5, and I get 650. Okay, so that does work. So the second part of the problem says use the results to predict the population year 2010. Well, 2010 is equivalent to t equals 10 because we said 2000 is t equals 0. So we plug in t equals 10. P of 10 is 548 e to the 0.03412 times 10. And I was trying to save time, but I think I ended up taking longer. So you get 770,000, or 770,000, or 770,000. Okay, so that's that one. The next problem is this continuous compounding, and I give you the equation. The amount in the account is equal to the amount that you put in, the principal, e to the RT, where R is the interest rate, yearly interest rate, and T is the time in years. So all you have to do here is solve for T. How many years will it take to increase the principal from 10,000 to 20,000? So, the principal is $10,000. The amount is $20,000. R is, so it's, I said it's 6%. I was demonstrating, it says 5% equals 0.05. That's just so that you know you need to use the decimal equivalent. So if you get 20,000 is equal to 10,000 e to the 0.06 t, we just have to solve for t like we did in the previous problem. So if you divide both sides by 10,000, you'll get 2 is equal to e to the 0.06t. Take the natural log of both sides. Use the properties of logarithms to bring out the exponent. The natural log of e is 0, so you get t is the natural log of 2 divided by 0.06. And I get 11.6, and the answer is in years because it says how many years, so it's 11.6 years. Okay, the last two, you're solving for x. This is one of those cases where you had to use the property of logarithms to combine two logarithms into a single logarithm. So because we have the negative sign, we can rewrite this as a quotient, the logarithm of a quotient. So that's the properties of logarithms. Now, you use the inverse properties of inverses to solve for x, to get into an algebraic equation. E to the natural log of x over x plus 1 is just x over x plus 1. And here I have e squared, which is 7 point whatever. E to the second power is 7.39. Okay, if we multiply both sides by x plus 1, get that. So that's x equals 7.39x plus 7.39. Subtract 7.39 from both sides, you'll get negative 6.39x is equal to 7.39. Divide both sides by negative 6.39, and you get negative 1.16. But if you go back to the original equation, which you always have to do in this case, see if this solution works. You know, some of the cases we've ended up with quadratic equations, and one solution is positive and one solution is negative. In this case, there's only one solution, and that solution is not doesn't work. So you would get a negative here, a natural log of a negative number. So no solution would have been the right answer. And then the last problem, 22, it's kind of like the previous ones, except you have to do a little algebra correctly. So the first thing you have to do is have the 7 combined with the 9 so that you only have 3 times the natural log of 5x. So I'm going to subtract 7 from both sides. That leaves us 3 natural log of 5x is equal to 2. Then you divide both sides by 2, so you'll get 2/3 here. And now once you've got this coefficient here as 1, then you can now use the inverse properties of logarithms and exponents. So we take e to the natural log of 5x, e to the 2/3 power. E to the natural log of 5x is just 5x, and e to the e to the 2/3 power is 1.948, or divide both sides by 5, 0.3895. Let's just plug it back in. 3 times the natural log of 5 times 0.3895 plus 7 should end up equaling 9. So let's do this. 3 times the natural log of 5 times 0.3895 plus 7. And I get 8.99999, approximately equal to 9, which agrees with the original expression. Okay, so that's the solution.